Here is the theorem. The recursive strategy that was defined in the slide before in terms of the max, which is recursive, has here an explicit strategy in tau, and n is n tau squared. All right. I think I'll skip this and I'll skip the next slide because I don't want people, I don't want the chair to stand up too early. Okay, now this Wythoff game was defined on two piles of tokens. Now the question is, can you generalize it to more than two piles? So people had been trying to do that in various ways, giving rules like take from any two the same number, or take from all three the same number, and all these kinds of proposals. But none of those preserves the spirit of Wythoff game. What do I mean by the spirit of Wythoff game? That Bn minus An is equal to n. That's one thing. And the second thing is that you have n tau and phi integer part. So the phi of tau is lost in these. So I suggested that the right way of doing it is what's here one, namely that a plus b plus c in nim sum is 0. So nim sum, I assume that everybody knows what nim sum is, but if not, then it's a summation over GF2 if you're an algebraist or whatever, and if you're a computer scientist, then you simply call it XOR. And this is a generalization of Wythoff, because if C is 0, then A nim sum B equals to 0 means that A must be equal to B. You take the same number from both piles. And that, okay, now let's go on. We want to investigate the structure of the P positions for the case where we have just 3 piles. And we write the P position in this form: J, A and J, B and J, where J is fixed, and then we let A and J and B and J go to infinity, and we want to observe their behavior and structure. So the claim is that under the rule 1, Wythoff strategy is almost preserved, almost, in the following sense: A and J, B and J almost split positive integers, and I'll come back to explaining that. And A and J is almost a mix of A, I, J, B, I, J, as before, but with the almost. And B and J minus A and J is 1, but only asymptotically. But whereas in math, often asymptotic means you have to go at least halfway to infinity, here you have to go only for the case J equals 1 to 23. And then it increases as J increases, but the moderate case. So I want to explain a little more of the almost preservation. And yes, so you see, for J, you remember this 1, 2 was in red, it was a P position for Wythoff. Now therefore 1, 2, K is an n position in the 3 Wythoff, 3 pi Wythoff. Why is that? Because you can take, one of the moves is that you can take from 1, maybe I neglected to say that, so I'll say it now, that from any single pile you can take as many as you want. And so from 1 to K you can go to 1 to 0. But 1 to 0 is a P position, and therefore 1 to K is an n position for every K of these 2. And we arrange them in non-decreasing order. And therefore 2 cannot appear in the list of p positions of 3 pi Wythoff. And therefore, you cannot have that the union of a and j and b and j is all the integers. 2 will be missing. And in fact, for j equals 1, three numbers will be missing. So, but it's almost okay, except that 3 are missing. And now the question is, if 3 numbers are missing, does this change the structure of these complementary sequences very much or little? What's going on? So a small set X of integers is excluded from the union of A and J, B and J. How does this affect, if at all, the structure of the complementary sequences? So I had these 2 conjectures. For every fixed j, there exists an integer nj and finite set x, such that for large n bigger than or equal to nj, a and j is a max of xj union a, j, b, j for I less than n. So in other words, the x is excluded. It's excluded by putting it into the next set. And b and j is equal to a and j plus n for large n. So this is preserved from the 2 pi Wythoff. And then the second one is that for every fixed j, there is an integer gamma j, such that for all large n, you have that n, a and j is it's either n tau minus gamma j or minus 1 and plus 1. So you get 3 different values rather than a single one. Rather than, before we had for the case of 2 pi Wythoff, we had a and j is equal to n tau. Here we have a fixed shift by gamma j and then the perturbation minus 1 plus 1, oscillation if you like. So for watching these conjectures, we investigated the splitting system perturbed by x, by this small set of numbers. And just so that I don't lose you too early, or maybe I lost already many of you, I want to recall the definition for the case of 2 pi Wythoff. an is a mix of ai, bi, and bn is an plus n. And then the sequences A and B, capital A, capital B, are complementary. And they're also n tau and n tau squared. Now we have this finite set X. And we define A prime over n, the max. And B prime n is A prime n plus n. And again, A prime is a sequence of those, and B prime is a sequence of the B prime. And let capital N be the maximum term of x plus 1. Then it can be shown that A prime, B prime are n upper complementaries for some n0 bigger than 1. N upper complementary means that from n on you have everything is split. And we want to relate A prime to A and B prime to B. In order to do that, we define the shift sequence, which is the difference between AN, which is the unperturbed sequence, and A prime N, which is perturbed by this X. And then we have this term that, again, there exists some integer P, such that for all n bigger than or equal to p, as I pointed out, for j equals 1 with just 23, either Sn is equal to gamma for all n, or else for all n, you have this triple oscillations. Gamma minus 1 you get, gamma and gamma plus 1. And if the latter holds,